Hello and welcome to the Wave Characteristics and Simple Calculations video. For the Waves unit, this is video 1a. When we're talking about waves in physics, we need to be sure that we understand which type of wave we're talking about because there are many different types and they all act a little bit differently. To start with, let's take a look at what wave motion is. Over here on the left, you can see that a rock of some sort was dropped into the middle of this area of the lake. So if you're standing on the edge and you're the one that dropped this rock, how come all of the water is not going to come from the lake and come to you on the shore? What's going on there? You would think, I mean, you can see the water moving towards you. How come it's not enough to make all of the water move forward? And what's going on there? Well, the biggest reason, and this is one of the important things that we have to keep in mind about waves and wave motion, is that wave energy travels along the medium through which the wave is traveling. But the individual particles of the wave just move up and down. They don't go along the medium. So in other words, the energy from the wave, the energy that was given the water from the rock, is going to go out in all directions. But the particles themselves are not going to do that. So the wave energy travels along the medium, but the particles of the medium just travel up and down. I don't know why my pen is going goofy there with the R, but so this is why we don't actually get wet when there are ripples coming at us from the middle of a lake. Now, if the ripples are big enough, it might cause the water to move a little bit so that you get wet, but in general, that's not because the water from where you started the wave is coming towards you and is going to destroy you, because the wave particles, the water particles, are not moving across the water towards the shore like the wave energy is. And that's an important distinction. So if we take a look here, rather than trying to slow down ripples coming from the middle of a lake, if we take a look at how we produce a wave on a string, for example, we take our string and the first thing we do is we make it move upwards. So we apply a force upwards on it, which of course makes the rope go up. And then that energy that made the rope go up is going to travel across. And as it travels across, the rope that did go up is now going to start to go down when we move our hand down again. And then the upwards part is going to move over to the right. And then this continues as the energy moves along. Now the rope is still there. We haven't lost the rope. It hasn't gone flying out of our hand or anything. The particles are moving up and down. The energy is moving from the left to the right. So we can see, if we study a single wave pulse, that the wave pulse is begun with a vibration and it is transmitted through internal forces within the medium. So again, remember, all types of traveling waves transport energy. It's the method of transportation that can be different. Now, continuous waves start with vibrations also. And if the vibrations that are started in a continual fashion, in other words, if we continue to go up, down, and then from here we go back and go up, down, and then back, and we just keep going around and around and round. If those vibrations are in simple harmonic motion, meaning that they are periodic, then the wave becomes sinusoidal. And this is typically what we like to think about when we think about a wave. Not the best sinusoidal wave there, but a sinusoidal pattern like that, where the particles are going up first, then the particles are moving back down over time. This is going over, and those that were up are going to be coming down. Let's get a better picture of this for you, though. And let's take a look at some of the characteristics that we're talking about with this continuous waveform. All right, so first of all, here's a much better drawn sinusoidal wave. First of all, we have the amplitude. The amplitude symbol is typically a capital A. It is the maximum distance from the rest position, either upwards or downwards, that the medium goes, that the particles go in. So again, it's from the rest position. So if this is our 0 point, it goes up this particular height, y, and then y would be our amplitude. Okay, let's say that that is 1 meter. All right, so this is from rest to max point or minimum point. It is typically measured in meters. Sometimes we talk about it in millimeters or in nanometers, but it's a length measurement, so it's some sort of form of meters. A wavelength. The wavelength of a wave is symbolized with lambda, the Greek letter for L for length. And wavelength, again, is typically measured in a meters of some sort. And it is the distance from one spot on a wave to the next identical spot on a wave. For example, if we look at the picture, we can say, all right, right here, we have a maximum. The next maximum is here. So the distance between them is a wavelength, lambda. We don't have to pick maximums. We could pick minimums. We could pick nodes here, but if we pick a node, we have to be careful because this node here is crossing the zero line on its way up. This next node is it is crossing the zero line, but not on its way up, it's on its way down. So it's not identical to the beginning point. The beginning point is, however, identical to here, where it's going up again. So we could measure it from a node to a node, as long as we get the correct nodes. We could measure it from anywhere, really. I mean, we could pick this point that's halfway between the 0 point and the minimum, and we get the same point again along the way. But again, here the wave is going up, here the wave is going up, so that is a wavelength. So again, the wavelength is essentially the length of one wave. And again, it's measured in some sort of a meter measurement. Oftentimes it's in nanometers as opposed to regular meters. And nano, remember, is times 10 to the negative 9. We then have a couple of other words here that are related to amplitude and wavelength, so I want to mention them now. The maximum point on a wave is called the crest. The minimum point is called the trough. A couple of other characteristics of waves that we need to talk about. One is the frequency and its related buddy there, which is the period. Frequency has a symbol of a lowercase f. Period has a symbol of a capital T. It is not a lowercase t because lowercase t stands for time, and that would get way too complicated. Yes, period is a time. However, it's a specific amount of time, so it has a specific type of t to go with it. Frequency is the rate at which a wave passes a particular place in space. So frequency is a rate of something, so that means it's waves per second. Well, waves isn't really a measurement, that's a counting item. So really it's 1 over seconds, which has a definition, is defined to be 1 hertz. The abbreviation for hertz is capital H, lowercase z. So again, the frequency is the rate at which waves pass you. It's how many waves go past you in a second. Sometimes it's given with how many waves go past you in a minute or an hour, but in order to do calculations with this, you want to change them into seconds. And that 1 over seconds is also called a hertz. Now, a period is related to a frequency because a period tells you the time it takes for one wave to pass a particular point in space. So it's seconds per wave. So they are inverses of each other. So frequency is 1 over period, or you could think of it as period is 1 over frequency. Period, of course, is measured in seconds. And again, it's the time for one wave to pass a particular place. So our last characteristic that we need to talk about that we can use for most types of waves that we're going to deal with is the wave velocity. If we know we have a wave, we have energy moving in a wavelength, and it is traveling at a particular rate, then we can find out that speed or the velocity of the wave. So the velocity of the wave is the frequency times the wavelength, or as it's written here, wavelength times the frequency, it doesn't matter, but v is equal to f lambda, which is telling us that we can find out how fast a wave is going if we know its wavelength, and we know the frequency with which it goes by, which if you think about it makes sense because wavelength is measured in meters, frequency is measured in 1/seconds. So meters times 1/seconds is meters per second, which gives us a speed. So with these 4 major characteristics of waves, we can take these and apply them to different types of waves. In this picture here, we have 2 types of waves. The motion of the particles in a wave can either be perpendicular to the wave direction, as they are shown in here in A. So here in A, the hand is going up and down, and so the particles are going up and down, but the wave energy is moving from the left to the right. These sorts of waves are called transverse waves. The way I like to remember this, that this is a transverse wave, is the T in transverse is similar to the perpendicular sign, which is what is true about the direction of motion of the particles versus the direction of motion of the wave. So we have transverse waves. And the other type of wave we have is the wave where the motion of the particles, which is back and forth, is parallel to the direction of the wave motion. And these are called longitudinal waves. So transverse waves, we tend to think of them when we think of waves. This is what we think of. They are the particles are moving perpendicular to the direction of motion. Longitudinal waves, we don't typically think of any waves like this, but it's sort of like an accordion or a slinky being moved back and forth. Light waves are an example of transverse waves, whereas sound waves are an example of longitudinal waves. So let's take a look at an animation of a transverse wave so you get a better idea of what this actually looks like. So if you look here at this transverse wave, you can see that the particles are moving up and down. Okay, they're going up and down. And you can see that the energy of the wave is moving from left to right. Now, none of the particles are moving from left to right. They're all just moving straight up and straight down. So this is what a transverse wave looks like. Now let's take a look at a longitudinal wave. Now, in this longitudinal wave, because it's a little bit more difficult to see just the particles and what's going on with them individually, we can see there's a little bit more detail here on this animation. We can see that the wave is moving from left to right as indicated by the black arrow at the bottom of the screen. And then they've got a few random particles made into red that are moving back and forth. So again, the particles are moving in a parallel direction to the direction of motion of the wave. Now, they aren't always going in exactly the same direction. Sometimes they're going with the direction of the wave, and sometimes they're going opposite the direction of the wave. But regardless of that, they are still moving parallel. Now, there's a couple of other words on here that are important as well: compression and rarefaction. A compression is an area where the particles are squished together. They're the darker lines, vertical lines that you tend to see appear, that's what appears to be moving across the screen. Those are compressions. The parts in between them where the molecules have more space to spread out are called the rarefactions. And this is, as we saw in the picture a minute ago, what makes a longitudinal wave longitudinal, because the motion of the particles is parallel to the motion of the wave. And in this picture, the rarefactions are called expansions. We don't typically call them expansions, we actually call them rarefactions. Okay, let's take a look at some other wave types other than just light and sound. We have the top picture here is talking about seismic waves, earthquakes. An earthquake produces several types of seismic waves, each causing extensive degree of damage. Now, right now we're not studying earthquakes, we're not going to look into the damage that they cause, but if you take a look at what's happening within them, in these 3 pictures, you can see how there are both longitudinal and transverse waves within an earthquake. Both types can travel through solid material, but only the longitudinal waves can propagate through a fluid. In the transverse direction, a fluid has no restoring force, so it wouldn't come back. to where it came from, which is what you need for the longitudinal wave. Which is what you need for the transverse wave. So this is one way that we can figure out where earthquakes come from, because the different layers of the earth, of course, are made up of different types of solids and fluids. And since only the longitudinal waves can go through a fluid, you're not going to get all of the waves at certain points on the Earth's surface where we have detectors, and you will get them other places. So that indicates whether the wave had to go through a fluid part of the Earth or not. So we have the P waves. The P waves, or primary waves, these are longitudinal. They alternate between compressing and expanding the rock. They are generally felt as a bang or a thump. So again, P waves are longitudinal. We also have S waves, which are called secondary waves. They are slower and stronger. They arrive after the P waves because they are shaking the ground clockwise and vertically. These are your transverse waves. They cannot go through the core because these waves cannot exist in air, water, or molten rocks. So the S waves are our transverse waves, because as you can see, the wave is moving from left to right, but the ground is moving up or down as it is passing. Then we have surface waves. Surface waves are what we call Rayleigh waves. As it's shown above, it is a circular wave. It has very similar uniform properties as to water waves, and it can cause severe damage to larger structures because the surface wave is going to go up and down and up and down, and it basically is trapped near the Earth's surface, and the earthquake's energy travels horizontally. So the surface waves rolling from the rocky basins are usually long and slow rolling waves. If it's strong enough, they are mostly a threat to the larger structures, such as bridges, because as you can see, a long bridge here is not going to be able to withstand its ends being raised while its centers being blocked. However, the smaller house will not have a problem just riding out the wave. So those are earthquake waves, both a combination of longitudinal and transverse waves. We also have water waves, and within water waves, we have a couple of different types of waves. They are very similar to the surface waves of earthquakes. Slight difference here, though, is the direction of motion. You will notice that the water waves are traveling clockwise, and the surface waves of earthquakes are traveling counterclockwise. And that is a distinction that's important to make. The water waves are not always circular. When the water waves are not circular and they are deeper than the surface waves, they get compressed a little bit. Surface waves for earthquakes are typically not circular, as this picture shows. They are typically much more oval, and those are the Rayleigh waves. So even though water waves appear to be similar or the same thing as Rayleigh waves, they are not, because they are in two different directions, and because water waves, when we're talking about the surface, is circular. And the water waves are clockwise in motion, and they are causing the water to rise up and then go down again. And the reason that this circular motion is disrupted as we get close to the shore is because the lower waves, which are traveling at the same time, are now getting bumped up. So this lowest wave is no longer able to, all of that energy has to go somewhere. Some of it is absorbed into the shore. Some of it, however, goes up, which will disrupt the circular pattern or the oval pattern at the mid depths, which cause it to slow down a little bit more, which causes the top surface wave to be faster than the water underneath it, which is where we get waves to break for us when we go to the beach. So of all of these types of waves, most of them that we're going to be dealing with are going to be longitudinal or transverse. I just wanted to make sure that you understood that we have other waves out there that sometimes are transverse, sometimes are longitudinal, but they don't always fit all the exact same patterns. All right, so now let's look at the relationships between these characteristics so that we can solve some problems. So again, as I said before, we have that frequency is equal to 1 over period, and the units for frequency are hertz, and they of course are going to be equal to the units for 1 over period, which is 1 over seconds. And of course those can be reversed. So period is 1 over frequency, so seconds is 1 over hertz. Then we also have the speed that we had said, that v is equal to f lambda, where v, remember, is speed, and it is typically figured out into meters per second, which is sometimes a problem because oftentimes your frequency is not just going to be in hertz, it's going to be in megahertz or gigahertz, and your wavelength is going to be in nanometers or micrometers. So you got to make sure that when you're solving for speed that your frequency is in hertz and that your lambda is in meters, or you're going to get all screwed up. These relationships here are relationships that hold true for any of the waves that we are going to be talking about. There's another relationship that is important when we are talking about waves that are produced on a string. And for waves on a string, we have a slightly different formula for the speed that we use because the string itself is going to affect the speed with which the wave can travel. So that relationship is that v, the speed, is equal to the square root of the force of tension on the string over what you would call the linear density or mass per unit length of the string. So again, F of t is the tension on the string. M over L is the mass per unit length of the string. Essentially, it's how much mass does each, say, meter of a string have, because that will determine how many molecules you have to try and get moving there first. So these relationships, really, there's three of them. F equals 1 over t, v equals f lambda, v equals the square root of ft over m over l, are the ones that we are going to be using to solve our problems in this unit. So let's get to some of those problems now. First one, what is the wavelength of middle C on a piano if its frequency is 261.6 hertz? Well, that would be great and easy to find because we know that V is equal to F lambda. So lambda is my wavelength, so that's what I want. So lambda is equal to V over F. Great. I don't know V. So what is speed? Well, this is the speed of what? The speed of the wave. This is sound. We're talking about middle C on a piano. So the speed of sound is what we're looking for. In general, we will use, unless you're given some more specifics about this, which we'll get to shortly, we are going to say that the speed of sound is 343 meters per second. This is speed of sound at room temperature. We'll come back to that in a little bit. So the speed of sound at 343 meters per second. So now we can say, all right, lambda is V over F. That's what we're looking for. Plug and chug, 343 over 261.6. We find out that the wavelength of middle C is 1.31 meters. So that means that if we draw the sound wave like a transverse wave, which I know it's not, but if we draw it like that, then the distance from one point to the next identical point would be 1.31 meters. Really, it should be drawn like a sound wave, so a sound wave would have compressions, and then rarefactions, and then compressions again. In this case, the wavelength would be from the beginning of the compression to the beginning of the compression, and that distance there would be 1.31 meters. All right, let's go to the next one. A radio station broadcasts at 100.1 megahertz. This is a capital M, so it's mega, not a little m, which would be milli. What is its wavelength? So again, we still want wavelength, so it's the same formula as before, but now I need to make sure that my frequency is not in megahertz, but in hertz. So again, I would say my speed is 343 and my frequency is 100.1 times 10 to the 6th, because mega is times 10 to the 6th. And when I solve that, I end up with 3.43 times 10 to the negative 6 meters. I don't like to write times 10 to the negative 6 meters because there's a better abbreviation for that. And that would be that it is 3.43 micrometers. So teeny, teeny, tiny. Amazing difference between the sound produced by a piano and the sound produced by a radio station. This has to do with what the purpose of a radio station is versus what the purpose of a piano is. And we'll come back to talk more detail about how radio stations actually work and why their sounds have to be at such a high frequency, but so a really tiny wavelength. What is the speed of a water wave if you see 12 waves with a wavelength of about 20 meters go past in 1 minute? All right, well, what is the speed of a water wave? So I want to know V. I know that I see 12 waves per minute. Well, that looks like a frequency to me, so I want to change that to waves per second. So I know that in 1 minute there are 60 seconds. 12 divided by 60 is 0.20 waves per second, or that will be my frequency. So now I have my frequency. I want my speed, so I need to look at my wavelength here. So V is equal to F lambda. F we just said was 0.2. Lambda we said is about 20 meters. So our water wave is traveling at a speed of about 4 meters per second. So again, the key here is to make sure that you recognize 12 waves in a minute as the frequency and convert that frequency to hertz. Let's do one more. The distance between two telephone poles is 40 meters. The wire's mass per unit length is 0.5 kilograms per meter. If the vibrations cause a wave to travel between the poles and back in 1.5 seconds, and the wire is rated up to 1500 newtons, will the wire break? Okay, so here's the question about, we've got telephone poles, we've got wires between the telephone poles, and now a big wind comes across, vibrations go by, and now there's a wave traveling on the wire. That wave is energy. That energy is going to cause changes in motion, and that is going to affect the tension in the wire, whether the wire is moving up and down, and the speed at which it's doing that. So the question is, can this wire withstand this sort of vibration without breaking? So first of all, we are looking for the tension. Well, we know from the equation a few slides ago that the speed, when you're talking about a wave on a string, and a wire is close enough to a string, the speed is the square root of the force of tension over m over L. So I rearrange that, and the force of tension is then V squared times m over L. V, we don't have V yet, but what we do have, remember that speed is distance over time. We have that the wave is going down and back in 1.5 seconds. So it's going a total of 80 meters in 1.5 seconds. So the speed of the wave is 53.33 meters per second. So 53.33 squared times 0.5. The reason I keep this as 0.5 is because remember we're looking for force, and a force is a Newton, which is a kilogram meter per second squared, so we need to keep that in terms of kilograms per meter. So 53.33 squared times 0.5 is 1,422 newtons is the amount of tension that the wire will feel. Well, that is less than 1,500, so it will not break. So again, this problem doesn't necessarily look all that much like a wave problem, but it tells you that there are vibrations that are causing a wave. Even if they didn't say that there was a wave and it just said vibrations were traveling from pole to pole, you should automatically assume that they are then talking about a wave and use the equation with wave and the tension, force, and the mass per unit length. All right, this should give you a chance to get started on the first assignment. So see you soon. Bye.